Hello, good morning everyone. Welcome. It's a real pleasure for me today to introduce Davide Massari to you, who is giving our talk today. So Davide did his studies in Bologna, both the degree in physics, astrophysics, astrophysics, okay, and the PhD within the group of Professor Francesco Ferraro. And after that, he spent a couple of years in the Netherlands, working with INAF. And since 2020, he is a staff at the University in Bologna. So Davide is very known for his work on globular clusters, the galactic globular cluster. He's been pioneer also the techniques in photometry with high spatial resolution cameras, and is well known for coupling Gaia and other surveys to try to distinguish the different building blocks of the Milky Way and assessing which globular cluster came from which building blocks, which I guess is also part of this topic of this talk today. So Davide is visiting within the framework of the Fundación Jesús Serra visitor program. He arrived this Monday, and he will stay here the full month of October until the 31st. So you are welcome to talk to him and interact with him, especially PhD students. And for you.
Right, thank you, Matteo. So good morning, everyone. First, please let me thank the Fundación Jesús Serra program and Matteo, because it's thanks to them that I'm here for this whole month. So again, please feel free to drop by the office I'm in if you want to discuss about what I'm going to talk about today, which is globular clusters as tracers of the Milky Way assembly history. So I will start the talk with a question, which is, how did the galaxy become like what we see today? So basically, this sum of components, we have a thick and a thin disk, the central stellar concentration that we call the bulge, everything embedded in the stellar halo. Well, the best place to answer this question is by focusing on the stellar halo. And the reason for this is that according to lambda CDM, the large galaxies like the Milky Way have built up hierarchically. Meaning, as you can see from these embodied simulations, that all of these small galaxies end up merging onto the central galaxy, and the disruption of this galaxy end up in building up the halo of the central galaxy. Now, in order to disentangle the individual contribution to this built-up process, one of the best way to go is to use dynamics. And the reason is that the individual contribution of all of the merger events tend to remain clustered together in the dynamical space described by conserved properties that are called integrals of motions, such as energy and angular momentum. So usually we don't see the debris of this merger event coherent on the sky because they have time to phase mix and to lose coherency, but we can, at least to a first degree, see some coherency in these dynamical spaces. Now, in order to measure these dynamical quantities, we need the 6D phase space information for our tracers, meaning we need the 3D position and the 3D velocity. And this means that very recently, thanks to the Gaia mission, we are experiencing a revolution in this sense. So historically, the most difficult parameters among the 6D phase space to determine were the proper motions. And now we know the proper motions for more than 1.5 billion of stars. And now, thanks to the combination of Gaia with other spectroscopic surveys, we have the 6D phase space information for millions of stars. And if you assume a certain shape for the gravitational potential, we can get the orbits of our tracers, as you can see in this beautiful picture here. Of course, we can get the orbits not only for stars, but even for other dynamical tracers, such as globular clusters. And here you see portion of the orbits of the globular clusters in blue, or dwarf spheroidal galaxies orbiting our Milky Way. And here you see portion of their orbits in red. So let's focus for a moment on this class of tracers, starting from globular clusters. So this comes from the compilation by Vasiliev and Baumgart, 2021. And here you see the distribution of the Milky Way globular clusters in a plane that shows eccentricity against semi-major axis of their orbit. Now, the main point I would like you to take away from this is that there's a large portion of the Milky Way globular clusters that move on highly eccentric orbits. Now, because of what I said before, that according to lambda CDM, we expect the Milky Way halo to have built up through merger of smaller galaxies, and because above a certain mass threshold, galaxies host their own system of globular clusters, we might expect that some of the Milky Way globular clusters were actually brought in by dwarf galaxies. And therefore, we should expect a dynamical link between the population of Milky Way globular clusters and the population of Milky Way satellites. So if we take the most recent compilations of orbital parameters for dwarf galaxies, such as the one by Giuseppina, you see that instead there are no dwarf spheroidal galaxies orbiting on highly eccentric orbits. So does this mean that the two populations are different? No, clearly no. And the reason is that the population of dwarf galaxies that we see today is clearly biased, because we are missing all of those that were created long ago and that are now completely dissolved within the Milky Way halo. Now, these are the characters of the Milky Way assembly. And so let's start discussing these characters from the main one, which is the Gaia Enceladus sausage dwarf galaxy. So these are the steps that led to the discovery of Gaia Enceladus. Everything started, of course, with Gaia, and in particular with the Gaia HR diagram, where you see the kinematically selected nearby halo clearly shows two sequences that run almost parallel one respect to each other. So in this HR diagram, you clearly see a bimodality. So what about if we move to the chemical space for the kinematically selected halo, where you see the same bimodality? Basically, you see some stars that describe this sequence that remains alpha enhanced up to a metallicity of about -0.5 and then starts to drop towards solar values. And then you see another sequence where this drop already begins at a metallicity of -1.5, so at lower metallicities. So, okay, we are convinced that the local halo is dominated by this bimodality, and then Gaia dynamical parameters came in. And this is what we found by looking at the dynamical space of the integrals of motions. So if we look at the distribution of stars here, we see three main features. First, that there are coherent overdensities here and there. And this is exactly what is expected we are expected to see in case of an halo that is built up via merger. But then again, we see a bimodality, because you see a pretty numerous population of stars here that move on orbit that are close to the circular orbits of the disk that are shown in blue, but a bit more eccentric. And then there's this blob, that is how we called it at the beginning. So there is a population of stars with slightly retrograde vertical angular momentum. And if we want to close the circle and understand the picture altogether, we select the stars belonging to that blob and we look at their distribution in the chemical space. And these stars are those that describe the sequence that has a knee point set at low metallicity. But the location of the knee point in this plot tells you something about the star formation rate with which the stars were formed. So the stars of the dynamical blob form in an environment that forms stars with a much lower star formation rate compared to that of the Milky Way, meaning these were formed in a dwarf galaxy. And this is Gaia Enceladus sausage. Now, what about the other population? So if you say, and these stars also describe the blue sequence of the HR diagram. So what about the other population? Well, the other population, so the population of stars that move almost on circular orbit, populates the high alpha sequence, and this tells us that they were formed within the Milky Way, and describe the red sequence of the HR diagram. And then CARMA found out that the two populations are actually coeval. So how do we interpret that? Well, we interpret the in situ population, the high alpha population, as the primordial disk of the Milky Way, that because of the encounter with Gaia Enceladus was dynamically heated up, so that the stars moved from the circular orbit to something a bit more eccentric. And then likely this encounter also caused some triggering of star formation that caused the newly formed stars to develop very soon a new disk, and this is what we see now as the disk. Good. So this is Gaia Enceladus sausage. After its discovery, many work tried to reconstruct the properties of Gaia Enceladus, and I would say there is a good agreement that the stellar mass is between 2 to 8 times 10 to the 8 solar masses, so this was a significant merger event, and that the accretion time is between 8 to 10 gig years ago. Now, after Gaia Enceladus, let's talk about the other characters of the Milky Way assembly history. And let's focus first on the retrograde portion of the halo, and you'll see in a moment why. So another important character is Sequoia. Sequoia was discovered by Myung and collaborators 2019, again as a coherent overdensity in the dynamical space that seemed to be systematically different compared to Gaia Enceladus in the chemical space. So in particular, Sequoia seemed to be a bit more metal poor and possibly enhanced in aluminum. So this caused the authors to interpret Sequoia as an independent merger event compared to Gaia Enceladus. But then, as soon as we could simulate the merge of Gaia Enceladus, it was immediately clear that the most external regions of Gaia Enceladus that are shown here in green and cyan are the first to be lost during the encounter, and they locate in a location of the dynamical spaces that coincides with the location of Sequoia. Moreover, if Gaia Enceladus behaved like the typical dwarf galaxies that we see today, and therefore if it had a metallicity gradient, that would also explain why the outermost regions are also metal poor. So then the question became, but are we certain we are looking at an independent merger event and this is not part of Gaia Enceladus? So to answer this question, it was necessary to add information, meaning, for example, to go to the detailed chemistry, to the detailed chemical abundances. And as you see from this work by Matsuno and collaborators, by looking at other elements such as sodium, magnesium, but others, it seems that Sequoia is indeed different compared to Gaia Enceladus. So at that point, there was good agreement that Sequoia is an independent merger event. They tried to reconstruct the properties of this Sequoia, and they found that its mass is smaller compared to Gaia Enceladus, between 5 and 9 times 10 to the 7 solar masses, and that its accretion time could possibly be even earlier compared to Gaia Enceladus, between 9 and 11 gigayears ago. But then Gaia EDR3 came in. Gaia EDR3 improved the kinematic measurement and therefore the dynamical parameters. And as you can see, we don't have anymore one unique coherent overdensity. We don't have one Sequoia anymore. We have 3. And you see those as the green, the red, and the blue dots there. Moreover, by looking at the metallicity distribution for a large sample of stars in the Sequoia region, Naidu and collaborators found 3 peaks that you see there here. So now the point becomes, is there a one-to-one relation between these 3 peaks and the 3 dynamical overdensities? What are we looking at? Are we looking at 3 different merger events at the same merger event? So again, to answer this question, we need to add more information. And one possibility is to add more chemical information. And this, in fact, is part of the project of my PhD student, Edoardo Ceccarelli. So basically what Edoardo would like to do is to try to unravel the complexity of the retrograde halo by looking at the detailed chemistry of halo stars. First of all, he had to select a large sample of retrograde stars when Gaia EDR3 was not out yet, so we didn't have the radial velocities. So we devised a method that do not rely on the radial velocities to select with very high purity retrograde stars. So as you can see from this tumor diagram, now to build this diagram, you need the 6D phase space information. So you also need the radial velocity. And here you see in blue, for example, these stars, and then we have halo stars. But then if you color code these stars by the transverse velocity, which is the velocity projected on the plane of the sky, for which you only need proper motions and distance, you see that by imposing a lower limit of 400 kilometers per second, you select retrograde stars with 95% purity. So we use these criteria to select about 200 stars that were observed with the high resolution spectrographs UVES at the VLT and PEPSI at LBT. But this survey is ongoing. We are still gathering spectra for more stars as we speak. And so the first attempt Eduardo made was to try to unravel the complexity in the Sequoia region, because then DR3 came out. And DR3 complicated things even more, because now we have 4 overdensities in this region. So we have this cyan substructure, this orange one, the purple stars, and the blue ones, okay? So what Eduardo did was to determine the chemical abundances for 17 elements. Now here I'm showing just 3 as example of group of elements. So we have alpha elements here, iron peak elements here, and S process elements here. Things are complicated even from the chemical perspective. Still, I think we can get at least 3 conclusions pretty robustly. First, have a look at the cyan stars and the orange ones. They behave in the same way in all of the chemical elements we have analyzed. So our conclusion is that the cyan and the orange stars actually belongs to the same progenitor, to the same merger event. Moreover, cyan and orange stars behave differently compared to Gaia Enceladus, which is the green. So we think that this merged event that we call Anteus, because Anteus is one of the name that one of these overdensity was given, we think this is an independent merger event. This is the first message that we take from this. Second, have a look at the purple stars. They are all pretty metal poor, about -2.5, and their metallicity distribution is very tight. So tight that we believe this substructure might not belong to a dwarf galaxy, but rather to a globular cluster. Now, unfortunately, with 4 stars, we are not able to sample enough the chemical spaces where you typically look for globular clusters, so sodium, oxygen, magnesium, and so on. But we are still trying to improve the sample, to increase the sample. It's not easy, I should say, but I should mention that there's a recent work by Eduardo Balbinot, where he also focuses on this substructure, and the conclusions are pretty similar. And then, third message, if you look at what is now left of Sequoia, that are the blue stars, and have a look. So before, this was Sequoia, and now what is left of Sequoia is just this overdensity here. So Sequoia looks pretty similar to Gaia Enceladus everywhere except in a few elements. So whenever you want to demonstrate that something is the same as another thing, they have to match everywhere. But if you want to tell that the two are different, a couple of elements are enough. So you can see in magnesium, Sequoia seem to be, even from a statistical point of view, systematically underabundant compared to Gaia Enceladus. And the same is true for calcium and possibly in the S process elements. So our conclusion in this case is that we agree that Sequoia in the end is an independent merger event compared to Gaia Enceladus. Now, I think this showcases the complexity of the retrograde halo. It is very difficult to properly interpret what we see dynamically, if not by adding more information. But let's move on with the retrograde halo, and let's talk about another character that is Thamnos. So we discovered Thamnos again as coherent overdensities in the dynamical spaces by also adding the information on metallicity. We found 2 overdensities. We still don't know if the 2 belong to the same merger event or not, because unfortunately little information exists for Thamnos. But we are observing stars belonging to Thamnos, so hopefully we'll be able to tell something more about that. Currently, by looking at apogee stars, Horta and collaborators found that Thamnos seemed to behave different compared to Gaia Enceladus. So likely Thamnos is another independent merger event. Good. Now let's move to the prograde halo. So I hope I've convinced you that the complexity of the retrograde halo is very high. If so, the complexity of the prograde halo is much worse. And the reason is that in the prograde halo we have the disk that complicates things even more. So in the prograde halo we have two very clear merger events. The first is Sagittarius. We see that on the sky because it has not yet phase mixed, so that is easy. And then we have the Helmi streams. So the Helmi streams were discovered by Amina in 1999 as these two overdensities in the velocity space. So you see these are specular in the vertical velocity because this shows you the wrap around the Milky Way. Attempts in modeling the progenitor of the Helmi streams say that its mass, it's about 10 to the 8 solar masses, and its accretion time is not very well constrained yet. It's between 6 and 10 gigayears ago. And now let's move on. It is very difficult to keep the pace with all of the discoveries of dynamical overdensities that came out on AstroPH every week. So the point that I would like to make is that we have to proceed with great caution in this case. First of all, we have to understand if the new discoveries actually are the same as some already existing ones, and this is not trivial at all. Second, we have to understand if these dynamical overdensities already belong to some existing known merger events or not. And third, we have to understand if these dynamical overdensities in the prograde halo are caused by the response of the disk rather than by some accretion event. So let's try to have a look at the most recent discoveries in this sense, starting from LMS1 and Wukong. So the two are the same overdensity. You see this overdensity in the dynamical space here, and you immediately see it is very nearby Gaia Enceladus. So by looking at the chemistry, what Horta found by using apogee data is that it is not very clear that LMS1 and Gaia Enceladus are so different. So it might be that LMS1 Wukong actually belongs to Gaia Enceladus rather than being an independent merger event. And then we have Pontus. Pontus is located here, so very nearby Gaia Enceladus and very nearby LMS1 and Wukong. And if we look at its chemistry, so you see here purple stars are Pontus stars and cyan stars are Gaia Enceladus stars. To me, this chemistry looks pretty similar. So again, it could be that Pontus is not an independent merger, but rather something related to Gaia Enceladus. And then again, we have Nix. Sorry, this is flip. The angular momentum is flipped. We have Nix here and Aleph here. Fortunately, in this case, the chemistry clearly says that these two overdensities were born in situ in the Milky Way. So these likely were caused by the response of the disk to some other accretion event. And then we have many others. We have Icarus, we have the Atari disk, Typhoon, C2, CD1, RL3, and others. I won't go into the details of this. Again, my main point here is whenever we talk about dynamical overdensity in the prograde halo, let's go with caution. Good. Now, we went to all of these assembly history, starting from a question between the link, about the link between globular cluster and dwarf galaxies. And now I hope I've convinced you that these links exist because many of the accreted dwarf galaxies were actually moving on highly eccentric orbits. So this link exists, and this means that we can try to associate the individual globular cluster in the Milky Way to their former progenitor. And this is what we try to do here, and the way to do so is basically to compare the location of the globular clusters in the integral motion space with the location of the stellar debris of this accretion event in the integral motion space. Because we know from theory and simulations that globular clusters trace stars. Now, associating the globular clusters to their progenitor means that we can also understand which of the Milky Way globular clusters were actually formed in the Milky Way. And to do so, we used an information that is crucial and that I have not talked about yet, that is the age of the globular cluster. Now here you see the distribution in the age metallicity plane of a sample of about 60 globular clusters with existing age measurement. Now it is well known from theoretical models and from previous literature that globular clusters moving on circular orbits describe a branch of the age metallicity relation that is clearly separated from the branch described by halo globular clusters. So what we did was to select the globular cluster along this metal-rich branch and use them to define the dynamical criteria in order to determine which globular clusters formed in situ. And by doing so, the criteria that we used is that these globular clusters are those that are moving with a vertical height smaller than 5 kpc and a circularity larger than 0.5, so moving along circular orbit. But in situ globular clusters are also bulge globular clusters, and we define bulge clusters as all of those whose orbit is entirely confined within the size of the bulge. So basically, those for which the apocenter is smaller than about 3.5 kpc. And then a cut in apocenter translates into a cut in energy. By doing so, we found out that about the 50% of the Milky Way globular clusters were born in the Milky Way, and the 50% was accreted from outside. At the time, this was a bit surprising, but then several simulations, cosmological simulations, showed that for Milky Way-like galaxies, the expected fraction of in situ to ex situ the globular cluster is just about 50%. So this was a nice confirmation about what we found. And at this point, we can focus on the accreted portions of the globular cluster. And we can try to associate them to their former progenitor, as I said before. So we start from Sagittarius. So Sagittarius is easy. We see that on the sky. And these in green are the globular clusters associated to Sagittarius. And then, by comparing the location of the globular cluster with the location of the stellar debris, we associated globular clusters to Gaia Enceladus. You see them here. To the Helmi streams, same game. To Sequoia. Thamnos would be here. It has no associated globular cluster. So this supports the idea that Thamnos is a pretty low accretion event. And at this point, we have associated the globular cluster to all of the known merger events that I talked about. And yet, there are still unassociated globular clusters that are the black points here. So let's focus first on this clump of coherent globular clusters, because coherency in the dynamical space might mean common origin. And we knew from the age metallicity relation that I showed you before that these clusters are in fact accreted. So we believe that with this group of globular clusters, we have actually discovered a merger event that was not discovered by using stars, because this is very much in the inner galaxy, where the extinctions make Gaia struggle in determining good kinematical measurement. Moreover, Krausen and collaborators 2019 predicted the existence of this merger event, but at the time it was not yet known, and this is why they called it the Kraken. So I think that this shows you the power of globular clusters as tracers of the Milky Way assembly history, because they're very powerful wherever stars are not powerful enough. And to support the idea that with globular cluster we have discovered the Kraken, let me show you this work by Horta and collaborators again, where they basically took stars in the inner galaxy that are located in the same region of the Kraken globular clusters in the dynamical space. So by using Apogee, they looked at the chemistry of these stars, and they found among these stars a population showing the chemistry of typical accreted stars. So to be completely fair, these authors called these substructure, this population of accreted stars, in a different way. They called it Heracles. But I think this goes back to one of the issues that I discussed before. We have to understand if different names actually refer to the same object. Now, in my opinion, but this is my personal opinion, this is just the case. And the reason why I say so is the following. So we have associated 20 plus globular clusters to Kraken. That means that Kraken was a very significant merger event. So a significant merger event means we expect to see in the inner galaxy a significant debris from the stars of this merger event. So what is the chance of looking at the inner galaxy, finding an accreted stellar debris and that not being associated to the most significant one? I think the chance is low, but the other authors are not convinced yet, so we might need some more evidence in order to answer this doubt. And then, finally, we are still left with these unassociated globular clusters shown in cyan. These are unassociated because these are very large distances. And this is the other place where globular clusters works better than stars to trace the Milky Way assembly. Because at these large distances, Gaia struggles in providing good parallaxes and good proper motions. So it might very well be that these globular clusters will soon tell us something about the accretion history in those distant places, at least until Euclid or Rubin will tell us more about the stellar debris at those distances. Okay, so by using our associations, Krausen and collaborators also describe the most recent merger tree available for the Milky Way. And to summarize, this is the table that associates to each individual globular cluster its likely former progenitor. But watch out, it is very much possible to improve upon these associations. So one way to do so is to use improved kinematics, because this was done with Gaia DR2, but then Gaia DR3 came out. And this is in fact what has been done by Cunningham and collaborators and Malan and collaborators. So there are ways to improve upon this, not only because of improved data, but because simply sometimes the debris of different mergers overlap in the integral motion space. So whenever we are at the boundaries of one of these, the associations are uncertain. And to solve these uncertain cases, we might need to add information, as I showed you before in the case of Sequoia. One possibility is to add chemical information, but another possibility that is very powerful for globular clusters is to add information on the age. And to show you why it is so important, let's have a look at the age metallicity relations that we built by only having age information for about 60 globular clusters, not even half of the entire population of Milky Way globular clusters. So in this case, everything is color-coded according to the former progenitor. And as you see, theoretical age metallicity relations are not drawn such as to fit the data. But these were actually built by using the structural parameter available from the literature, and you see how well they reproduce the data of the globular clusters. And yet this is done only with a small sample of globular clusters. So, and whenever, I must say, whenever one combines different compilation of globular cluster ages, severe systematic errors have to be taken into account. And this gives you an example of that. So these two are the two largest compilation existing of globular cluster ages. One is by Forbes 2010, and one is by Vandenberg 2013. These are the globular clusters in common. And you see that as soon as we select globular cluster more meta-rich than -1, we have to face a systematic of 2 gigayears. And 2 gigayears is not negligible for this kind of studies. So this triggered a dream, an idea. Why don't we try to get homogeneous ages for the entire sample of Milky Way globular clusters? And this is what we are trying to do now within the CARMA project, and I'm very happy to talk about that because this includes many people here like Matteo and CARMA. So CARMA stands for Cluster Ages to Reconstruct the Milky Way Assembly. The idea is to build the first complete sample of very homogeneous globular cluster ages. And this dream has recently become more concrete because we were awarded more than 100 orbits with HST to observe all of the globular clusters that have never been observed with HST. So now we will have a unique photometric system to observe our globular cluster and to estimate our ages. So let me give you a showcase example of why ages are so important. So this is what we published yesterday. You might have seen that on the AstroPH. But this is a simple case that I think shows you perfectly why it is important to get homogeneous globular cluster age. Let me talk about this pair of globular cluster, and this is 6388, and then this is 6441. And let me talk about their origin. So if we only focus on dynamics, what I would say is that 6388 is born in situ, and 6441 was accreted. But then, still, if I were to use not the distance coming from the Harris catalog, but the distance coming from Baumgart catalog, I would conclude the opposite. The 6388 is accreted and 6441 is in situ. Now, Cunningham and collaborators, on the other hand, concluded that both are in situ. So no, dynamics doesn't help much in understanding the origin of this pair of clusters. Let's have a look at chemistry. So Horta and collaborators, by looking at alpha elements, concluded that 6388 is accreted and 6441 is in situ. But then Minelli and collaborators, by looking at another set of chemical elements that are very talkative, that are scandium, vanadium, and zinc, concluded that 6388 is accreted and 6441 also. But then Carretta et al., using the same elements, concluded the opposite, that they're both in situ. No, chemistry is not enough. Let's see if age is enough to solve this mystery. Spoiler, it is. So what we did was to select, first of all, 4 globular clusters for which we clearly knew the origin. We selected 4 globular clusters that we knew are in situ because all of the dynamical evidence and the chemical evidence says that they are born within the Milky Way. And we select them because they are at the same metallicity as our 2 globular clusters. So the idea was the following. Let's determine the age for this sample of 6 globular clusters. If that pair of globular clusters were born in the Milky Way, it should be coeval with the other 4 globular clusters. Otherwise, they should be younger by at least 2 gigayears according to the age metallicity relation. So we selected HST photometry, we cleaned the column magnitude diagram by means of proper motion membership, and we tried to get rid of any possible systematic errors in the analysis. For example, by correcting for differential reddening, and you see here the differential reddening map. We got rid of any peculiar population in globular clusters. So some of you might know that these 2 globular clusters are very peculiar. They have helium-enhanced populations and C plus M plus O enhanced populations. And so we didn't want to fit their column magnitude diagram. We got rid of them and fit the CMD only of the standard population. And then we corrected the theoretical models that we are using, that are the ones from Basti, for temperature-dependent extinction effect. So after all of this, we ran our isochrone fitting code, and this is what we found. So in black are the 4 in situ globular clusters, and in white are the pair that we are investigating. They are coeval, and therefore they were born in the Milky Way. And another evidence supporting this is the comparison that we made with the location in this age metallicity space of halo stars as found by CARMA. So you see here, this is the branch likely associated to accreted stars, and this is the branch that is associated to stars born in situ. And our globular cluster matches very well the location of in situ stars there. Good. So I am moving to my conclusions. I hope, well, to have convinced you that we are now experiencing a revolution in understanding the Milky Way assembly And the more we go on with investigating, the more we found out complexities and difficulties. So to face them, we need to add more information. We need to add the chemistry, we need to add the age, or sometimes we need to change the tracers to move from stars to globular clusters, especially where extinction is an issue and where distance is an issue. Now, within the CARMA project, we will try to determine a complete and very homogeneous set of globular cluster ages to try to help disentangle what is still to be unraveled of the Milky Way assembly. And I stop here, but first, please allow me a bit of advertising to tell you that we are organizing this conference in Bologna that is called the Milky Way Assembly Tale, Plot and Characters as of today and what to expect from future editions. It will be held in Bologna in the last week of May next year. So if you're interested in the topic, I very much hope that you will be interested in participating. Thank you very much for your attention.
Thank you very much, Davide. So we have time for some questions.
So I had a question about whether, is it possible that globular clusters were at one point in their history hosted, like all non-globular clusters at some point were hosted by a dark matter halo that underwent a disruption? Or can this formation event be excluded in some cases?
So I wouldn't say that understanding if globular clusters were formed in their, you're talking about their own individual dark matter halo, right?
Yes, so this dwarf galaxy that got disrupted and we have this remnant core scenario. I think it's not necessarily the whole case of, basically does not account for all the cases, right?
Well, I think rather than looking at the dynamic of the individual globular cluster, I would look at their stellar streams. So if there were some dark matter halo around, this would hamper the stream itself. So by looking at the extension of the stream or at the fact that the stream exists or not, that would tell more, I think, about that.
Okay, thank you.
Thank you for the wonderful talk. I wonder if in the age metallicity plane, we should really be able to distinguish between different accretion events, because the age metallicity relation may be very close, really. So what do you think?
Yes, that depends on how good we are in determining our ages. No, so if you look at this, there are slight differences. So the parameter that drives the shape of these age metallicity relations is mass. And if you look at the least massive accretion events like Stream and Sequoia, what happens is that the most metal poor globular clusters are a bit younger compared to the more massive accretion events. But I think we are talking about a few hundred mega a year. So that will be tough. But you know, until someone tries, there's no way to find out. So, I mean, I think we aim in the end at a few hundred mega years in terms of relative age. So I wouldn't exclude that it's possible to see some differences.
There is an empirical relation between the number of globular clusters and the stellar mass of a dwarf galaxy, well, of galaxy in general. So, for those globular clusters, you think that they come from a particular dwarf galaxy accretion event? Do they comply with expectations, or do you have an idea?
Yes, they do. I might have a slide about that. So this is for Gaia Enceladus only. Among all of the progenitors, the one that is more off with respect to the expectation of these relations that you talk about is Sagittarius. So Sagittarius seem to have an higher specific frequency compared to its mass, while the rest of the progenitors seem to lie along the typical relations that are observed.
So it means that after one of these accretion events, all the globular clusters, they survive? None of them,
That's a good
gets
point.
dissolved?
Yeah, that's a good point. I think the chance is high, and the reason is that they were orbiting within a dark matter halo that shielded them from total disruption, because they came in within the dark matter halo of their own progenitor, and this, especially in the first orbit, saves them from start disruption. Then, as soon as the dark matter halo of the host starts becoming less dominant with respect to the Milky Way field, then the globular cluster starts to disrupt. But I think they don't have enough time to totally disrupt. This is how I would interpret this fact, at least. But it could very well be that some are disrupted and we are not seeing them yet.
Can I ask a second question? Or? Okay, it's about the age of the second generation in globular clusters. Could you comment on that? Are they different from the ones that you're getting for the main one?
Yeah, so that depends. That depends on the. So observationally speaking, the differences that have been found are always within 100 or 200 mega a year. And sometimes they have been found to be coeval. So from 100 or 200 mega a year downward as a difference. And this is important to try to understand what is the reason for these peculiar populations, because there are scenarios that says that they should be coeval and scenarios that predicts a small difference in age. I think the most recent asteroseismologic measurement of a difference between the two globular cluster population in M4 is of 120, 140 mega a year.
Thank you. Very nice talk, very interesting. You said, and I agree, that it's quite difficult to know if this Kraken Heracles koala is actually the same progenitor or not. But as you know, it is not the only possibility to have these populations as a residual supercritic systems. And here is when the aurora process appears.
Yeah.
And you didn't mention at all, but you wrote that it's an inconsistent explanation.
Yes.
Could you please elaborate a little bit more?
Yeah, thank you for asking. As you know, basically the definition of aurora comes from a purely chemical criterion in order to define what is in situ and what is ex situ. So the reason I am writing here that this is against what they find is that that definition sets boundaries in the dynamical spaces that exclude Kraken globular clusters from being ex situ. So if you only look at they look at the chemistry, they select accreted stars according to their chemical criterion, and from these stars they define dynamical criterion. According to that dynamical criterion, the Kraken globular clusters should be in situ, but the age metallicity relations said the opposite. So in my opinion, using aluminum only can work in general on a large sample of stars, but will miss some individual cases.
Yeah, I see, but this is not actually what they do. Actually, what we do is to fit at the same time kinematical properties and all the chemical planes. Right?
But not for the globular, for the stars.
Yeah.
But for the I'm talking for the globular clusters. No, tell me if I'm wrong, but you set the aluminum cut at minus 0.075.
Yeah, roughly.
You look at where the globular clusters are in the dynamical space, and then you draw your dynamical selection, right?
Yeah, which is somehow different what Danny's paper does, which is including extra cuts in aluminum that, in my opinion, is a little bit contradictory if you want to separate population in situ and ex situ origin. So, but we can discuss maybe.
Yeah, maybe. I would be glad to do so, yes.
So I have a comment and question. So the comment is about Sagittarius. You were saying that Sagittarius has a weird globular cluster populations compared to the
Sorry,
other.
Sagittarius?
That Sagittarius has a weird globular cluster populations in terms of number. But there is two things there. First of all, we don't know exactly what is the number of globular clusters in Sagittarius. It's still debating between 6 to 9.
Yes, that's true.
And also one of the things which is interesting, like regardless if it is 6 or 9, is that almost actually all the globular clusters in Sagittarius are in the trailing arm of Sagittarius and not in the leading arm, which is also something which is very interesting because it can lead to some problematic behaviors in the dynamical imprint to be able to follow the evolution in energy angular momentum of an accretions inside it. So which is something I think which is interesting.
I totally agree. Very
to
much
see
so.
and to study there.
Yeah.
And so the question that I have is, why do you think that if Kraken exists, why do you think it's one only accretions? Because in the area where it is, you have just a pile-up of every accretion possibility, so you can know with your age metallicity relation if it is accreted or in situ. But then, except if you get an evolution of the, not only of the action, but of the angles, you can really know if it is from one accretion or not.
That's a very fair question, and the reason why I think it's one is because it's the simplest way of interpreting one subtraction. But it might very well be that it's not only one, that there are more. So your doubt is absolutely fair, and I don't have a question actually, an answer actually to that. I suppose we would have to find the stellar debris and look at the properties of the stellar debris, maybe the chemical properties. But as you saw, even in chemical spaces, stuff are very, very difficult to interpret.
Well, I mean, even in dynamical debris there, it will be really hard because everything is phase mixed. Not only spatially mixed, but really phase mixed there.
Yes.
So it will be extremely hard to still get a signature, even of an accretion of 6 or 8 years.
Yes, yeah, you're right.
Okay, I think we're running out of time, and it's also as a reminder, we have a scientific coffee afterwards, so if you want to keep talking with Davide. And let's thank him again.